Machine language and assembly code. In this video, we're going to discuss computer machine language opcodes and operands, assembly language, and then we're going to be the computer. Machine language is the binary coded instructions that's built directly into the CPU of a particular computer and is used directly by the computer. Machine language is the only language that the computer understands natively. Higher level languages, such as Perl, Python, Java, are all translated into machine language before they can run. Every processor family has its own set of instructions. For example, Intel has processors that are dedicated for desktop machines. ARM has a set of processors that are dedicated to cell phones. The relationship between the processor and the instructions it can carry out is completely integrated. Every machine language instruction does only one very low-level atomic task. Machine language instructions can be broken into two pieces, the opcode and the operand. The opcode specifies one low-level task for the CPU to process. In this course, we're going to be using opcodes that are 4 bits long. So 4 bits will give us a total of 16 different instructions. Machine language instructions will have 0 or more operands, and in this course, most of the instructions will have one operand. You should have in front of you the machine language instruction set printout. You can either have printed it out or have it on the screen. As you can see, there are 16 different instructions here, 16 opcodes, 16 mnemonics. They're numbered from binary 0 through binary 1111, 0 through 15. Each opcode represents one mnemonic. So opcode 0 says load whatever is in location X into the register. Opcode 0110 is a decrement. It says take whatever in memory location X and subtract 14 from it and store the value back into X. So on this chart, wherever you see X, that refers to the contents that can be found at memory location X. So here's sample memory. We've got 10 different memory locations, 10 different memory addresses, and their contents. We have 0, 1, 2, 3, 4, 20, 21, 22, 23, and 24. This is in binary. This is what's being stored internally to the computer. Now, how do we know if what we're looking at is program or data? And the answer is, depends on what we do with it. If we decide to run it, it's a program. If we decide to manipulate it, it's data. We're going to be using instructions at address 0 through 4 as programs. So we're going to divide it up. So the first 4 bits are our opcode, and the remainder is our operand, which will be the address that we're working with. So program and data. And over here is a reminder of what our instructions are. So opcode 000 is a load, and it says take whatever at location 10110, which we can find over here. The middle one is this, and we're going to store that into a register. So opcode, operand, everything's in binary. Not the easiest thing to manipulate. So instead, if we look at it as decimal numbers and mnemonics, we would see this. At address locations 0 through 4, we have our program. At locations 20 through 24, we have some data. load what's in location 22, in this case the value 23, put it in the register. Add what's in location 20 to the register, take what's in the register and store it in location 21, and then print out what's in location 21. Short description of what this program does. Writing in machine language is difficult. So people will typically write their machine language programs in assembly, and they will then run it through an assembler to produce the machine code. So we would take our machine language assembly program and produce machine code that the computer can directly work with. So remember our 4 steps of the instruction cycle: fetch, decode, do it, and then move on to the next instruction. Well, we're going to apply that to our machine language program. And let's see how we can do that. All right, so we've been looking at this program that has 5 instructions: a load, an add, a store, an out, and then a halt. So let's look at what it does. We're going to be the computer. And the way we're going to do that is we're going to put our values into the program counter, special register, the general register, register R, the instruction register of the processor. Each processor also has comparison register, which we'll talk about more in the next video. So, looking at the fetch, interpret, execute, and increment as our cycle. We're going to start off, and our program counter is going to start at location 0. And 0 has load 22. So we're going to fetch that instruction. Now we're going to do load 22. So that was our fetch. What does that mean? Well, let's interpret it. Load 22 says take the value that's in location 22, address 22, and store that value into the register R. Well, we can see that address 22 has a 23 in it. So let's put that 23 into the register. That's our execute. So we fetched the instruction, we figured out what to do, we did it, and now we're ready to increment to the next pointer. So 1 becomes, the next pointer is address 1. So we're back to our instruction cycle again. Now we're back to fetch. So at address 1, we see an add 20. So we're going to take and erase what's here in the instruction register, and we're going to say add 20. Okay, what does that mean? Let's interpret it. Add 20 says take the contents of address 20, which is a 3, and add it to the register and store it back in the register. So we're going to take the value 3 and put it into the register R. Well, 23 and 3 is 26. So we're going to make 23 into 26. So we fetched the instruction, we figured out what to do, we interpreted it, we executed it, and now we're ready to increment our program counter. So address 1, we're now going to go to address 2, the next address. And since we're not focused on that, we'll erase this. So at location 2, we have a store 21. So we're going to get rid of what's in the instruction register right now. And we're going to fetch it and put it here. And what does store 21 mean? Well, let's interpret it. Store 21 says take what's ever in the register and put it into memory location 21. So right now there's a 26 in the register. We're going to take that and we're going to get rid of what was there and put the 26 into location 21. And that was our execute. And now we're ready to increment the pointer again. So we're going to go to instruction number 3. And we're going to fetch instruction 3. So we need to get rid of what's in there. and we're going to fetch it. So out 21. And what that means is we're going to take the contents of address 21, which is the value 26, and display it on the screen. So let's draw a screen up here. And the address 21 has the value 26. So we'll display that there. And that was our execute. Now we're ready to come down and increment our program counter. So we're going to make that into 4. And we're ready for our next instruction. So instruction 4 has a halt. So we're going to get rid of this and insert halt. There's no operand. Well, it turns out that the halt is a different sort of instruction. It does not take an operand. It just says, my program's done. Every assembly language program, every machine language program has a halt as its last statement. If you didn't, the computer wouldn't know to stop at instruction 4. And it would just continue going. It would go to instruction 5 and find whatever was there and try to execute it. And then it would go to 6 and take whatever was down there in 6 and try to execute it. So last instruction needs to be a halt. And we're done with our program. So you should still have your mnemonic instruction, your machine language instructions set in front of you. All right, we're going to be the computer again. So here's a situation where we've got the program counter, and it says our next instruction is 5. The register already has a 4 in it. The last instruction was decrement, and the comparison register is at 0. We've got memory addresses 100, 101, 102, and 103, and 100 has the value of 11, 101 has the value of 94, there's a -3 in 102, and there's an 8 in 103. So if we're going to be the computer, the first thing is to fetch the instruction. So program counter 5, fetch. Our program has a clear 101, so the first thing is put that into the instruction register, fetch it. We need to interpret it. The clear 101 says put a 0 in whatever location is specified by the operand. So this location 101 is going to go from 94 to 0. All right, that was our execute. Now we need to increment the pointer to the next instruction. And instruction 6. Now I'm going to clear this a little bit differently so we can do several steps together. So right now our program counter has a 6 in it. And it says we want to add 103. So step 1 is fetch. Add a 103. What an add does, it says take the value stored at 103 and add it to the register. So there's an 8 in 103 right now, and there's a 4 in the register, so 8 plus 4 is going to give us 12. That was our execute. Now we need to increment our pointer to the next location, location 7, and 7 has a store 102 in it. So we need to fetch our store 102. Okay, step 2 is interpret. What does it mean? It means take the value that's in the register and store it at the location specified by the operand. All right, so we're going to get rid of this -3, and we're going to put a 12 there. So that was our execute. We need to increment our pointer to the next instruction. And that's all we have at the moment. All right, that's the end of this video. The next video that you're going to watch is translating assembly code to Perl. If you have any questions, send me an email or come to my virtual office hours.